Welcome to your first lesson on quantum programming. Today, we dive into the world of qubits and quantum gates. By the end of this course, you will write your own algorithms. Before we start quantum programming, we need to understand the smallest unit of information, the bit, and its quantum version, the qubit. A normal bit is simple. It is like a coin lying on a table. It can show only one clear result, 0 or 1. In classical programming, every value is built from bits. The bit is either 0 or it is 1. There is no in-between. A qubit is different. Imagine a coin that has not landed yet. It is still spinning, rotating, or falling through the air. While the coin is spinning, we do not yet have a final answer. The qubit is in a state that can become 0 or 1 when we measure it. Measuring a qubit is like catching the coin and forcing it to land. After measurement, we see one result, either 0 or 1. But before measurement, the qubit can have different chances of becoming 0 or 1. It is not always 50-50. Sometimes the qubit is rotating in a way that makes 0 more likely. Sometimes it makes 1 more likely. Sometimes they are equally likely. So a qubit is not just a random coin. It has a special quantum state. That state controls the probabilities of the final result. Now comes an important idea: phase. Two qubits can have the same probability of becoming 0 or 1, but still be different. Think of phase like the direction of the coin's rotation. One coin may rotate this way, and another may rotate the opposite way. If we measure them immediately, they may look the same. But if we apply a quantum operation, the phase can change the final result. This is why phase matters in quantum programming. It is hidden during direct measurement, but powerful when we modify the qubit. The first major concept is superposition. Superposition means the qubit is not fixed as only 0 or only 1 before measurement. Using our coin example, superposition is like the coin spinning in the air. It has the possibility of showing 0 or 1 when it lands. But remember, this is not just a normal coin spinning very fast. A qubit has quantum probabilities and phase. The second concept is entanglement. Entanglement happens when two qubits become linked as part of one shared quantum state. Imagine two coins falling together. If one lands on 1, the other may also land on 1, or it may always land the opposite way. The important idea is that their results are connected. We cannot fully describe one coin without talking about the other. The third concept is interference. Interference happens when quantum possibilities combine, strengthen each other, or cancel each other. Using the coin idea, imagine one motion pushing the coin one way and another motion pushing it the opposite way. If the motions work together, the effect becomes stronger. If they oppose each other, they can cancel, like stopping the coin's movement. In quantum programming, interference is how we increase the chance of correct answers and reduce the chance of wrong answers. So the bit is like a coin that already landed. A qubit is like a quantum coin still in motion, with probability and phase. Superposition is the spinning possibility. Entanglement is the link between coins. Interference is when their motions add or cancel. Once we understand these three ideas, quantum programming becomes much easier to follow.